Okay, so if you're watching this video, we've probably just had our first Chem 258 class, and we only had time to go over the syllabus, and there was a little bit of information that I wanted to go over from one section of chapter 12, which we're starting with, and a couple sections of chapter 14. We're actually going to cover the bulk of chapter 14 later, much later in the semester. But these two sections or two or three sections really belong, I believe, up at the beginning of the semester where we're talking about spectroscopy because they're relevant to that subject. And you probably did a little bit of spectroscopy in Gen Chem. I used to teach Gen Chem a very long time ago, and we did a little bit of ultraviolet visible spectroscopy. And you might have done some in Gen Chem lab, and you certainly did some IR spectroscopy in Organic 1 lab. So spectroscopy, as I said, is the subject that we're starting this semester with. So it's helpful for us to know what is spectroscopy and why do we do it. So let's start the slideshow from the current slide. In general, whenever you're doing any kind of spectroscopy, the first thing you have is a sample. And that sample will be exposed to electromagnetic radiation of some type. And you're familiar with the electromagnetic spectrum. You know it goes all the way from X-rays and gamma rays at the very high energy, low wavelength end, all the way up to radio waves at the very low energy, long wavelength end. So, right. And so the idea is the molecules in the sample absorb some wavelengths or some frequencies of that radiation. And when they do so, they undergo what's called a transition, which is a reversible change. Generally, it's reversible. Generally, it doesn't involve breaking bonds or anything like that. And that reversible change is called a transition. And the type of transition that the molecule undergoes depends upon the type of electromagnetic radiation. And so then there's a detector on the far side of all of this that tells us which wavelengths or which frequencies of that radiation got absorbed. And from that, we get information about the structure of the molecule. And the type of information we get is based on the type of radiation that we used in the experiment. So the reason that we do spectroscopy is to either find or verify the structure of an organic compound. And from each different type of spectrum, we get different types of information. We're going to start with ultraviolet and visible spectroscopy. The order that we are going to cover the types of spectroscopy in is the order, in my opinion, of going from least information to most information about the actual structure of the molecule. And that's certainly debatable, but I'm just going based on my opinion of going from what gives us the least information to what gives us the most information. And I think there's no doubt that ultraviolet visible spectroscopy gives us the least information, which is why I'm going to spend very little time on it and why I don't mind covering it in a video rather than in class. And so after this, we'll cover infrared spectroscopy. That will be Wednesday. That'll be next class. We're also going to cover something called mass spectrometry. You'll notice the word's a little different. It's mass spectrometry. People sometimes call it mass spectroscopy, but really that's wrong. Mass spectrometry is based on a different principle, and we'll cover that on Friday. And then we'll cover a couple different types of nuclear magnetic resonance or NMR spectroscopy. That's going to be where we get the most information about a molecule. But when organic molecules absorb either ultraviolet or visible light, the type of transition that they undergo is at the level of the electronic state. And what happens is that the molecule will absorb a photon of either ultraviolet or visible light, and an electron will get excited from a lower energy molecular orbital to a higher energy molecular orbital. Nearly always the transitions are either N to pi star, that is non-bonding, to pi antibonding, or from pi to pi star, pi bonding to pi antibonding. And in general, it's a transition from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And you probably covered those terms in Gen Chem. Even that's not really what I wanted to focus on, but I wanted to make sure that we understood what the basis of the phenomenon is. And as I've said, UV-vis spectra are pretty broad and featureless. We get very little information from them. They used to be used a lot more, maybe back in the 40s, 50s, 60s, we didn't really have much more than ultraviolet and maybe infrared. NMR was just starting, so we took what we could get in terms of information. They're generally not used nowadays, except in very particular sophisticated fields. But we still can learn something about organic molecules using ultraviolet visible data, and especially by comparing one set of data to another. And what turns out to affect most of all the amount of energy that it costs to pop an electron from the HOMO to the LUMO, what seems to affect that most of all is the number of what's called conjugated double bonds in the molecule. And that's another reason that I like bringing this material up to the very front of the class. I really like having that term conjugated right here at the beginning of class. So we need to be able to distinguish among these three types of double bonds: isolated, conjugated, and cumulated, and especially look at this term conjugated. So the definition of conjugated double bonds is those that are separated by exactly one single bond. There's your definition. And again, I'm getting this all straight out of the class notes, the PowerPoint document that's available on Canvas. And in order to be conjugated, I do need to stress the double bonds don't have to be carbon-carbon double bonds. They can be double bonds between any elements. So here, for example, are two compounds that have conjugated double bonds. You'll notice they both alternate double, single, double, double, single, double. So those both have conjugated double bonds. We say those are conjugated molecules. In this molecule, the double bonds are not conjugated, they're isolated. They have more than one single bond between them. So these are not conjugated double bonds. This is not what we're looking for in ultraviolet visible spectroscopy. Very rarely you will see double bonds that are cumulated, that arise from the same atom. And I just wanted you to be aware that there is a word for that. It's called cumulated. But we're really going to be focusing on conjugated double bonds. And also, conjugated double bonds are going to arise for us quite a bit in the material in this class. So they, I think, are the most important class of what you run into with multiple double bonds. It's important when we see conjugated double bonds. Those should jump right out at you when you look at a structure, if you see any conjugated double bonds. And like I said, when you looked at ultraviolet visible spectroscopy in Gen Chem, you probably focused on making, what are those called? Oh, I'm totally forgetting my Gen Chem now, but you probably made a graph where you graphed absorbance versus concentration. I think they called them concentration curves. And you went and you found the molar extinction coefficient, and you had fun in that area. We're not really going to be looking into that too much right now, but I just wanted to point that out in case you'd used ultraviolet visible spectroscopy before. We're mainly going to be interested in what is the wavelength of the ultraviolet or visible radiation that the molecule absorbs the most at. Where's the wavelength of maximum absorbance? And we call that lambda max. That's going to be the wavelength of light that the molecules absorb the most. And it turns out that, other things being equal, the more conjugated double bonds are in a molecule, the lower energy of that lambda max, or longer wavelength, the lambda max will be. Remember, energy and wavelength are inversely proportional, right? E equals hc over lambda. So they're inversely proportional quantities. And so the more conjugated double bonds, the larger lambda max will be, and the fewer conjugated double bonds, the smaller lambda max will be. The reason behind that is unfortunately well beyond the scope of this class. You got to get into real serious quantum mechanics in order to explain that. But this slide is the bottom line. The other things being equal, the more conjugated double bonds, the higher lambda max is in nanometers, the fewer conjugated double bonds, the lower lambda max is in nanometers. And so organic compounds with no double bonds or only isolated double bonds absorb in the far ultraviolet. So we're talking 200 nanometers or less. And then as you introduce more and more conjugated double bonds into the molecule, that lambda max figure shifts more and more to higher wavelengths. So that number gets larger and larger. And eventually, if you add enough conjugated double bonds, the absorption will come out of the ultraviolet into the visible range, and it will start to absorb visible light, and the compound will take on a color. And I certainly don't expect you to memorize anything. That's not the point here. But I do have some examples here. Here's ethylene. Ethylene has just the one double bond. It absorbs in the far ultraviolet, below 200 nanometers. This compound happens to be called isoprene. I don't know if I care that you know that, but we have two conjugated double bonds. It absorbs at 220 nanometers, so we've moved to the longer wavelengths. 3 conjugated double bonds and we're at 250 nanometers. 4 conjugated double bonds and we're at 290. And that continues. We're getting closer and closer to that cutoff of ultraviolet versus visible light, which, as I recall, is round and about 400 nanometers, give or take. And an extreme example would be a molecule like lycopene, which has this structure that you see over here. There's 11 conjugated double bonds in this molecule, not including the couple of double bonds that are not conjugated to the system. And so this material absorbs blue light, and so it appears red to us. So its lambda max is 475 nanometers. That's in the visible range. That reminds me, I should call it ChemDraw and draw you one structure before we go on. But I can go even more extreme than this. But you can see that as you get more and more conjugated double bonds, that lambda max gets higher and higher. You certainly don't need to memorize any lambda maxes. That's not the point here. I'm not going to give you a structure and say, what is the lambda max? No. But I would expect you to be able to make comparisons between different structures and to be able to predict which is going to have the lowest lambda max or longest wavelength or shortest wavelength of absorption. Or I could also ask you to rank them in order of energy, highest energy to lowest energy, or lowest energy to highest energy. Remembering the lowest energy is going to correspond to the longest lambda max and the highest energy to the shortest lambda max. There is also one more section in this, section 14.9. You are not responsible for that section. It will never be on any of our exams. I do want to show you just one more thing if I can figure it out, because it relates to lab. So let's open ChemDraw and let's see if I can figure out how to do this. There is going to be a molecule that you're going to make in lab later on in the term that's really exceedingly conjugated. And it's called tetraphenyl cyclopentadienone. And so it looks like this. And of course, pH is just a shorthand for a benzene ring. So you're going to make this material in lab, and you can see that it's completely conjugated all the way through. It's got 4 benzene rings, which are, of course, conjugated, that are all conjugated to these 2 carbon-carbon double bonds in the 5-membered ring and to the carbon-oxygen double bond in the carbonyl. So this molecule is an extreme example of conjugation. And this molecule happens to absorb so far into the visible range that it almost looks black. It absorbs red light, and so dilute solutions of this appear purple. So you're going to make that stuff. It's kind of interesting. Anyway, I said I'd keep this video short, so that's basically it for UV-vis spectroscopy. It's not something we're really going to be using, but you can compare one molecule to another in terms of how many conjugated double bonds it has. The more conjugated double bonds, the longer the wavelength of maximum absorption in the ultraviolet and visible, and the fewer conjugated double bonds, the lower the wavelength of maximum absorption will be. And remember again, wavelength and energy are inversely proportional. The longer the wavelength, the lower the energy, and the shorter the wavelength, the higher the energy. If you can get that much out of these two sections, I'm happy. That's basically it. So that's about it. Thank you for tuning in. I will see you all in class.